In Shanghai, at a shipyard called Jiangnan, engineers are drawing up plans for a cargo ship that will carry 25,000 shipping containers at once. Stack that many containers straight up into the sky, and the pile would tower higher than 50 Eiffel Towers standing on top of each other. Now here's the part that sounds impossible. That ship is not being designed to run on oil or diesel or any fuel you could pump at a dock. It is being designed to run for 40 straight years without ever stopping to refuel, powered by a nuclear reactor small enough to fit where a submarine's reactor sits, using a fuel that almost nobody outside of a physics lab has ever heard of. By the end of this video, you will understand exactly how China plans to pull this off, why nuclear cargo ships failed every single time someone tried this before, what makes this new reactor different enough to maybe actually succeed, and what it could mean for shipping, trade, and the global economy if China actually gets there first. If videos about the strangest and biggest engineering projects on the planet are the kind of thing that keeps you curious late at night, hitting subscribe means you will not miss the next one. No pressure, just an open invitation for anyone who genuinely likes finding out how impossible-sounding ideas actually get built in the real world. For almost 70 years, nuclear-powered cargo ships have been a dream that kept quietly dying. Back in the late 1950s and into the 1960s, the United States built a ship called the NS Savannah, a beautiful, sleek vessel meant to prove that nuclear power could work for ordinary cargo and passenger routes, not just for warships hidden under the ocean. It sailed. It worked. And it was still a financial disaster. It cost far more to build than any diesel ship of its size. It cost even more to run. And almost no port around the world wanted a nuclear reactor quietly floating in their harbor next to fishing boats and ferries. Germany tried something similar with a ship called the Otto Hahn. Japan tried with a ship called the Mutsu. Both ran headfirst into the exact same walls that sank the Savannah. Enormous costs that never balanced out. Deep public fear of anything with the word nuclear stamped on the hull. And port after port simply refusing to let these ships dock at all. One by one, all three projects were shut down and quietly forgotten. For decades afterward, nuclear cargo ships were treated less like the future of shipping, and more like a cautionary tale engineers told each other about good ideas that could not survive contact with reality. So why would anyone try again 60 years later with the exact same core problem still sitting right in the middle of the idea? The answer comes down to two enormous pressures that never actually went away and have only gotten worse with time. The first is fuel cost and pollution. Modern cargo ships burn a thick, dirty type of fuel called bunker fuel, and the entire shipping industry is now under massive international pressure to cut emissions dramatically over the next few decades. The second pressure is range and raw power. A nuclear reactor can pull an almost unbelievable amount of energy out of a tiny amount of fuel, which means a ship could travel further, run faster, and skip the constant refueling stops that slow every diesel-powered vessel down today. The reactors from the Savannah era were heavy, expensive, and needed thick protective shielding just to be considered safe enough to sail, which is exactly why those old projects collapsed under their own cost. If someone could finally build a reactor that is smaller, safer, and cheaper than those 1960s designs, the whole idea might actually survive this time. That is precisely the gap China is trying to close, and the tool they are using is a type of reactor that barely existed outside of research papers until very recently. To understand just how much is riding on solving this, it helps to picture the economics of a single giant container ship making one trip across the ocean. A large modern cargo ship can burn well over 100 tons of fuel every single day it is at sea, and a round trip between Asia and Europe or Asia and North America can stretch on for weeks at a time. Multiply that fuel bill across an entire fleet, across an entire year, and fuel becomes one of the single largest costs a shipping company faces right alongside the ship itself. Now imagine a version of that same ship that simply never needs to buy fuel again for 40 years. Even if the reactor costs far more to build up front, the potential long-term savings and the total removal of fuel price swings that can wreck a shipping company's budget overnight is exactly the kind of prize that keeps engineers willing to try this idea again, despite 60 years of failure behind them. It is called a thorium-based molten salt reactor, and that name sounds intimidating, so let's break it down into something you can actually picture in your head. Think of an old-fashioned nuclear reactor like a pressure cooker sealed on your stove. It uses solid metal fuel rods, and the whole system runs under extremely high pressure, which is a big part of why it needs thick steel walls, heavy containment domes, and constant careful monitoring just to stay safe. A molten salt reactor works more like a slow cooker left simmering on your kitchen counter. Instead of solid fuel rods locked in place, the nuclear fuel is dissolved directly into a special salt mixture and kept in a liquid state at very high temperature, but crucially at normal, low pressure. Because there is no dangerous high-pressure buildup waiting to blow, the entire system can be built lighter, more compact, and with a far lower chance of the kind of runaway meltdown that made older reactors so frightening to the public. Now add the second ingredient into that slow cooker, thorium itself. Almost every nuclear reactor running today in power plants and submarines around the world uses uranium as its fuel. Thorium is a different radioactive metal entirely, and here is the twist. Thorium cannot power a reactor directly on its own. Engineers first have to convert a portion of it into usable nuclear fuel inside the reactor itself, almost like turning raw, uncooked ingredients into something you can actually eat, right there inside the same simmering pot, without ever having to open the lid. For decades, that conversion step was considered the single hardest part of the entire thorium dream, a step that mostly existed on chalkboards and in theoretical papers. China has already pulled it off in a real working laboratory reactor, successfully converting thorium into usable nuclear fuel while the reactor was actually running. That one result, more than any concept drawing or press release, is what convinced serious engineers that this idea might genuinely be ready to leave the laboratory and step onto an actual ship. Here is how the full chain is supposed to work aboard the ship itself, laid out step by step. First, the thorium-based molten salt reactor generates heat, roughly 200 megawatts of thermal power, which puts it in the same power class as the reactors used in some of the United States Navy's most advanced nuclear attack submarines. Second, that heat does not push the ship directly, the way burning diesel fuel pushes a piston. Instead, the heat is used to warm up carbon dioxide gas that has been squeezed into a special high-pressure state called supercritical, similar to compressing a gas until it behaves with the density of a liquid without ever actually turning into one. Third, this superheated, supercritical carbon dioxide spins a compact turbine, working on a similar principle to how steam spins a turbine inside an old-fashioned power plant, except this supercritical method packs far more energy into a much smaller, lighter machine. Fourth and finally, that spinning turbine generates electricity, and the electricity powers the motors that turn the propellers, quietly pushing 25,000 containers worth of cargo across an entire ocean. No burning fuel, no black smoke pouring from a stack, just heat, pressure, and a chain of spinning machines silently doing the job diesel engines have handled for the last century. There is one more piece of this mechanism worth slowing down for, because it is the actual reason engineers believe this design could finally survive contact with reality where the Savannah did not. Picture the difference between a sealed pressure cooker and an open slow cooker one more time. If something goes badly wrong inside a pressure cooker, the pressure itself is the danger, because it wants to escape violently all at once. A molten salt reactor never builds up that kind of pressure in the first place, so there is nothing straining to explode. On top of that, engineers can design these reactors with a simple, almost old-fashioned safety trick, a plug of solid frozen salt sitting at the bottom of the reactor that is kept solid only by a fan constantly cooling it. If the power ever fails and that fan stops running, the plug simply melts on its own, with no human needing to press a single button, and the liquid fuel drains safely down into a separate containment tank shaped so the nuclear reaction naturally shuts itself off. It is a passive safety system, meaning gravity and basic physics do the protecting, not a control room full of people making split-second decisions under pressure. That single design choice is a big part of why engineers today believe this technology is fundamentally safer than the reactors that powered and ultimately doomed ships like the Savannah 60 years ago. Sounds almost too clean and too simple to be real, right? So who exactly is standing behind this project, and how do we actually know it is more than just a few impressive-looking concept renders released for publicity? The company leading this effort is Jiangnan Shipyard, a subsidiary of China State Shipbuilding Corporation, a colossal state-owned company that alone controls roughly 1/3 of all shipbuilding output on the entire planet. This is not a hopeful startup running on venture capital and a slick website. This is one of the largest shipbuilders that has ever existed in human history. Lin Qingshan, the vice president of Jiangnan Shipyard, publicly confirmed the 25,000 container nuclear ship design at the Marintech China conference held in Shanghai, telling reporters from the South China Morning Post that the company wants to be, in his words, a front-runner in this field. He also revealed that construction of the vessel could realistically begin in around a decade, with some industry estimates pointing toward the year 2035 as a possible starting point. Separately, Hu Keiyi, a senior engineer at Jiangnan Shipbuilding Group, published detailed technical specifications in a respected Chinese trade publication called Ship and Boat, laying out the 200 megawatt thermal reactor output, the supercritical carbon dioxide power system, and a planned operational lifespan of 40 years for the reactor core itself. On top of that, Jiangnan has been working alongside China National Nuclear Corporation, the nation's top nuclear power authority, on a related, slightly smaller 14,000 container version built around the same underlying reactor technology, jointly unveiled as a preliminary design the year after the original 25,000 container concept first went public. Having two separate ship designs moving forward at once, one led by the shipbuilder and one co-developed with the National Nuclear Authority, suggests this is not a single team chasing one flashy headline, but a broader industrial strategy being tested from more than one direction at the same time. This is not happening in isolation either, and that matters for how seriously we should take it. Three major international ship classification societies, the American Bureau of Shipping, Det Norske Veritas, and Lloyd's Register, have all recently published detailed reports examining the real challenges and advancements around nuclear power for commercial shipping. In South Korea, Samsung Heavy Industries has partnered with the Korea Atomic Energy Research Institute on a competing concept for a nuclear-powered liquefied natural gas carrier. In March of 2026, the South Korean shipbuilder HD Hyundai signed a formal agreement with the American Bureau of Shipping to design a 16,000 container ship powered by nuclear-linked electric propulsion. Over in Norway, government maritime authorities and research councils have funded feasibility studies into nuclear-powered cruise ships and cargo carriers, and a firm called Ulstein has promoted its own concept for nuclear-powered polar cruise ships built around thorium reactor technology. When a company controlling roughly a third of global shipbuilding output, a national nuclear authority, three of the world's biggest classification societies, and multiple rival countries are all pouring serious engineering time into the same basic idea in the same handful of years, that stops looking like a publicity stunt and starts looking like the early stage of an actual industry shift. To put the scale of Jiangnan's ambition into perspective, the very first version of this idea, a nuclear-powered container ship capable of carrying 25,000 containers, was first announced all the way back in 2023. For the next 2 years afterward, the project mostly lived as a rough concept, a bold headline with very few hard numbers attached to it. That changed when Hu Kei's detailed article was published, finally putting a real reactor output, a real power conversion system, and a real projected lifespan onto paper for the first time. Going from a vague announcement to a fully specified 200 megawatt reactor design with a named engineer attaching his own name to the numbers is exactly the kind of shift that separates a marketing headline from an actual engineering program with real people accountable for the math. Concept drawings and reactor specifications on paper are one thing. Real progress inside a real physical reactor is something else entirely. So where exactly is the proof this is more than just very convincing paperwork? The clearest proof so far comes from that laboratory breakthrough mentioned a moment ago. Chinese researchers achieved stable, sustained operation of a working thorium-based molten salt reactor and successfully converted thorium into usable nuclear fuel while that reactor was actively running. That milestone matters enormously because it is widely considered the single hardest scientific hurdle standing between thorium reactor technology and any real-world use. And it has now been cleared inside an actual working system, not merely sketched out in a physics paper. Beyond the reactor breakthrough itself, Jiangnan Shipyard has already pushed the concept a step further, unveiling plans for something even more ambitious, a floating, nuclear-powered green marine transport hub. Picture an entire artificial island functioning simultaneously as a shipping port and a ship recharging station, powered by a blend of nuclear energy and renewable sources, purpose-built to service nuclear-powered cargo ships as they move through the world's busiest shipping routes. Jiangnan unveiled this floating hub concept at the Posidonia International Shipping Exhibition in Greece, one of the largest and most influential shipping industry events held anywhere in the world, describing the project as a new ecosystem for zero-emission ocean container logistics and a groundbreaking solution for decarbonizing the global shipping industry. None of this proves a finished nuclear cargo ship is quietly sailing somewhere already, but it does prove the underlying reactor science genuinely works inside a real laboratory, and that the surrounding infrastructure, the ports, the recharging stations, the entire support ecosystem is already being seriously mapped out right alongside it. There is also a quieter, slower kind of proof worth mentioning, the kind that does not make flashy headlines, but matters just as much to engineers. The International Maritime Organization, the United Nations body that sets global shipping rules, has been actively pushing the entire industry towards steep emissions cuts over the coming decades, with targets aimed at getting international shipping close to net zero emissions by around the middle of this century. That regulatory pressure is not going away, and it is a huge part of why classification societies like the American Bureau of Shipping and Lloyd's Register are spending real time and real money studying nuclear power instead of dismissing it outright. When the rulebook itself is quietly pushing an entire global industry toward a technology, that is a very different situation than one shipyard chasing a flashy idea on its own. There is also a symbolic proof point worth mentioning, the kind you cannot put a number on, but that engineers pay close attention to anyway. Presenting the floating nuclear hub concept at the Posidonia International Shipping Exhibition matters, because that event is not a domestic Chinese trade show. It is one of the most closely watched gatherings in the entire global shipping world, attended by ship owners, insurers, and regulators from dozens of countries. Choosing to unveil this concept on that particular stage, in front of that particular audience, signals that Jiangnan is not just building for a domestic Chinese market, it is actively trying to convince the rest of the world's shipping industry to take this technology seriously, right alongside them. Step back for a moment and think about what this could actually mean if the technology scales up the way its engineers hope. Global shipping moves close to 90% of everything traded around the entire world, and nearly all of that trade depends on burning fuel that pollutes the air and keeps getting more expensive as environmental regulations tighten year after year. A fleet of nuclear-powered cargo ships would not need to stop for fuel across entire ocean crossings, could run at consistently higher speeds without the constant weight of massive fuel costs dragging down every trip, and could operate almost entirely free of the smokestack emissions that traditional cargo ships pump into the atmosphere every single day of the year. For a country like China, whose entire economic engine depends on manufacturing goods and shipping them out across the ocean, being first to master this technology would not just be a scientific bragging right, it would be a genuine economic and strategic advantage over every other shipping nation competing for the same routes and the same customers. This also is not a race China is running alone in an empty stadium. It is the opening stage of a much bigger global competition. South Korea has its own molten salt reactor concept moving through development for gas carriers. Companies across Norway are actively studying nuclear-powered cruise ships and cargo vessels of their own. A major South Korean shipbuilder has already signed formal design agreements with an international classification society to chase a nuclear-linked container ship of its own. Every one of these countries understands the same basic truth. Whoever solves the cost, safety, and regulatory puzzle first does not just win a single contract. They set the technical standard the rest of the world's shipping industry ends up building around for decades. Right now, based on published lab results, named engineers, and confirmed public statements from company leadership, China appears to be several genuine steps ahead of everyone else at turning this idea from a concept drawing into working hardware. But is being first in the lab the same as being first on the open ocean? That is far from decided yet. There is one more layer to this competition worth understanding, because it is not only about who builds the fastest ship, it is about who other nations will actually trust. A shipyard can design the most advanced reactor in the world, but if foreign governments do not trust the safety record and transparency behind it, their ports may simply refuse entry, the same way ports refused the Savannah decades ago. That is part of why classification societies publishing independent safety reviews matters so much, and why countries like Norway and South Korea running their own parallel programs is not just wasted effort. It is each nation trying to build enough of its own expertise and trust to eventually operate, inspect, and approve these ships on equal footing rather than depending entirely on whichever country gets there first. Whoever earns that trust fastest may end up shaping the actual rulebook the rest of the world has to follow. Could an entirely new set of international shipping laws end up getting written specifically because of ships that do not even exist yet? That is looking more likely every year this technology keeps advancing. Here's the part most flashy tech videos conveniently skip over, and it genuinely matters if you want the full picture instead of just the exciting half. This project is difficult, expensive, and still far from finished. Industry experts, including engineers at the maritime technology firm BMT, have publicly pointed out that construction of the actual Jiangnan container vessel remains roughly a decade away at best. with global regulatory frameworks still nowhere near ready to support real commercial operation. Cost is an enormous unanswered question too. Nuclear fuel itself is remarkably cheap to run once a reactor is actually built and operating, but building and maintaining a nuclear reactor aboard a commercial cargo ship is extremely expensive up front, and industry voices, including Hu Kei himself, have suggested that government support may be absolutely necessary, since private shipping companies alone may not be able to shoulder that level of financial risk on their own. Then there is the regulatory maze, arguably the toughest wall of all. Nobody has clearly decided which government body would even hold the authority to approve a nuclear-powered commercial cargo ship sailing freely into international ports around the world. Every single country a ship like this wants to dock in would need to trust the safety standards of a reactor designed and built by a completely different nation, and after the very public failures of the Savannah, the Otto Hahn, and the Mutsu decades ago, public unease about nuclear-powered civilian ships has never fully gone away, even among people who otherwise support nuclear energy. This entire project could still stall out, get pushed back years past 2035, or quietly get scaled down the way so many ambitious mega projects eventually do once the real bills start arriving. Beyond cost and regulation, there are two quieter concerns worth taking seriously too. The first is training and crew safety. Running a nuclear reactor safely for 40 straight years requires highly trained specialists, and commercial shipping crews today are simply not trained the way submarine crews are, which means entirely new training pipelines and safety cultures would need to be built from scratch before any cargo company could responsibly operate a ship like this. The second concern is insurance and liability. If a nuclear-powered cargo ship were ever involved in a serious accident, a collision, a grounding, even a bad storm, figuring out who is financially and legally responsible for a nuclear incident at sea is a legal puzzle the shipping industry has never fully had to solve before, since nothing quite like this has operated commercially in decades. None of these problems are impossible to solve. But they are exactly the unglamorous, unfilmed kind of work that determines whether a brilliant reactor design ever actually leaves the shipyard. Even the historical failures deserve a second look here, because they are not just a footnote. They are the entire reason today's engineers are designing so differently. The Savannah, the Otto Hahn, and the Mutsu all used older, heavier reactor designs that needed thick, pressurized containment and constant expert supervision, which made every single voyage expensive and every port authority nervous. A molten salt reactor, running at low pressure with that passive, gravity-driven safety plug built in, is specifically engineered to avoid the exact weaknesses that sank those 3 ships decades ago. Whether that is enough to finally win over skeptical ports and skeptical governments a second time around is still an open question nobody can honestly answer yet, and it might end up being decided more by politics and public trust than by physics at all. So here's where all of that actually leaves us. China has revealed genuinely detailed, technically specific plans for a 25,000 container nuclear-powered cargo ship, backed by one of the largest shipbuilders on the planet and the country's own top nuclear authority. The core reactor technology, a thorium-based molten salt system, has already achieved real working success inside a genuine laboratory setting, not just inside a glossy concept drawing. But turning that laboratory success into a massive nuclear-powered ship actually crossing the Pacific Ocean is still roughly a decade of difficult engineering, enormous unresolved cost questions, and complicated international regulatory approval away from truly happening. If you want to keep catching breakthroughs like this the moment they surface, hit subscribe and tap the notification bell, because stories this strange rarely stay buried on the internet for long, and you will want to already be here for whichever one comes next. So tell me honestly, if a nuclear-powered cargo ship like this one actually sets sail somewhere in your lifetime, would you want to see one dock in a port near you, or does the whole idea make you a little nervous? Type your real answer in the comments below.